Today we're going to be talking about related rates. And our steps to related rates are, first we draw a picture about the situation. We're going to describe the situation with an equation. Write out what you know, write out what you want to find, and then in most cases we're going to take ddt of our equation and plug in what we know to solve. Now, when I say ddt, that means that we're going to be using implicit differentiation. We're not going to be taking, most of the time we're taking dy. Okay, we're finding the derivative of y. Now we're finding the derivative of, in most cases, time. We're going to be talking about a rate. That's why it's called related rates. Okay, our first example. Assume that oil spilled from a ruptured water tanker spreads in a circular pattern whose radius increases at a constant rate of 2 feet per second. How fast is the area of the spill increasing when the radius of the spill is 60 feet? Okay, so I want to know how fast area is increasing. So I'm looking for a rate because area increasing. Okay, so what do we have? We have oil spilling in a circular pattern with a certain radius. Okay, so rate an equation for what I'm trying to maximize or minimize, or not maximize, for my rate is area. Area is pi r squared. Now let's talk about what we know. The radius increases at a rate, so a derivative of 2 feet per second. So dr dt is equal to 2 feet per second. I want to know dA dt, that's what I'm looking for when r is equal to 60 feet. I can't plug in 60 feet right away because I need to know when it's at a certain instant. So I need to find the derivative. What we're going to do is we're going to take the derivative of this with respect to time. So the derivative of A with respect to time is dA dt. Pi is a constant. Derivative of r squared with respect to time is 2r dr dt. Now plug in what we know. We're looking for dA dt. We have 2 pi. Our radius at the instant is 60 when our radius is increasing at a rate of 2 feet per second. So simplifying all that out, we get 240 pi, and that is feet per second. So this is a cone example, and a lot of the cone examples are very similar. Suppose that liquid is to be cleared of sediment by pouring it through a conical filter that is 16 centimeters high and has a radius of 4 centimeters at the top. Suppose that liquid flows out of the cone at a constant rate of 2 centimeters cubed per minute. At what rate is the depth of the liquid changing at the instant when the level is 8 centimeters deep? Okay, so let's draw a picture. So we have our cone. We have our cone. Now the cone, the actual stationary cone, is 16 centimeters high and has a radius of 4 at the top. Suppose that we have something in here and the liquid is flowing out of the cone at a constant rate of 2 centimeters cubed per minute. So what we have to figure out is what is that? What part of our whole piece is that? We have centimeters cubed per minute. Honestly, what helped me a lot in these types of problems is centimeters cubed is a unit of volume versus time. I'm flowing out, so we are negative. Okay, I need to know the depth of the liquid. So I'm going to call that the height. So I'm looking for the depth of the height in relation to time when our height is equal to 8 centimeters. Notice how these pieces are all stationary. 16 and 4, the cone is always 16 high, 14 for our radius. Those are not changing, but the height and the volume are both rates, and those are changing. I'm looking for something when our height is equal to 8 centimeters. So we have our formula for volume of a cone. And since you guys are all good geometry students, you remember what that is. So then I need to get this in terms of one variable. Since I'm looking for dH/dt, I need to get rid of r. If I didn't get rid of r, I'd have a product rule, and I don't know how r relates to h in terms of rates. So let's look at what we have here. Okay, we have similar triangles. We have this black triangle, and then the inside, the little red triangle. So 4 is to whatever our radius is, as 16, the height, is to whatever our height is at our instant. I'm sorry, our height is in terms of just regular old h. I can't plug in these instants until I've taken the derivative. Can't plug in any of this instant stuff until I've taken the derivative, because the derivative is at an instant. So relating our radius, solving for r, we get h over 4. So volume is equal to pi over 3 h over 4 squared h. Now this simplifies all kinds of fun stuff in here. Pi over 48 h cubed. Now I take my derivative. Once I've taken the derivative, I can talk about what's happening at the instant. My derivative is pi over 16 h squared. I did some simplifying. Oh, I almost forgot my ADHDT. Don't forget, it's implicit differentiation when you're doing these. Now plug in what we know. dv dt, -2. I hate this blue line. I don't know why it's now on all my smart boards. It makes me angry. Anywho. H, our height, is at this instant. I can plug these now in that I've taken the derivative. H is the instant. H squared is 64 dh dt. So solving for dh dt, what do we get here? Oh, I solve and I get -1 over 2 pi. Don't forget your units. If I give you units, give me units back. Don't make up units if I don't give you units. But if I give you units, give me units back. And those units are going to be, height. Since our volume was centimeters cubed, our height is in terms of centimeters per minute. And notice how, again, the height is decreasing. That's why my rate is negative. And you'll have to watch that in the book. And when we do the examples in class, that's going to confuse some of you guys. And I want to show you what our book is doing to make sure you realize that the negative means something versus the wording in other questions. This example is a ladder example, or a right triangle one, where we have a ladder leaning against a wall, a 13-foot ladder. Make note that that 13 feet never changes. It's always 13 feet long. The top of the ladder slips down the wall at a rate of 2 feet per second. How fast will the foot be moving away from the wall when the top is 5 feet above the ground? So that's part A. And then part B is we want to know the rate at which angle theta between the ladder and the ground is changing. So we have our ladder, which is constantly 13 feet. So that's key. It's leaning against a wall. The top of the ladder, so this point right here, is slipping down at a rate of 2, so I'm going to put a little negative in there, feet per second. So then we want to know how fast will the foot be moving away. I want to know how fast this point is moving in that direction when we are 5 feet above the ground. So let's name some sides of our triangle. I named this guy X, I named this guy Y. So dx dt is equal to -2 feet per second. I'm looking for dy dt when x equals 5. Okay, so what you want to keep in mind, we now need to write an equation involving x, y, and 13. Well, hopefully you guys realize it's a right triangle. That's why our Pythagorean theorem is so helpful to us. So x squared plus y squared is equal to 13 squared. Okay, so now we need to take the derivative of this. So 2x dx dt plus 2y dy dt, derivative of 13 is 0. If I divide everything by 2, really I have x dx dt plus y dy dt equals 0. Now plug in. We know dx dt is 2 feet per second. I don't know what x is. We'll talk about that in a minute. Dx dt is -2. We don't know what y is, but we're looking for dy dt. We know we want to find dy dt when x is equal to 5 at that instant. So I plug in 5. Okay, how do I find y? Well, at that instant, when x is equal to 5, so when x is equal to 5, our hypotenuse is 13, we have a right triangle, and convenient that it's a Pythagorean theorem, so y is going to equal 12. It's a Pythagorean triple, I should say. Or you could use your Pythagorean theorem to solve. So solving that, we get -10 is equal plus, I should say, 12 dy dt equals 0. So dy dt, simplifying, is equal to 5/6, and let's get some units, feet per second. Now part B, at what rate is angle theta between the ladder and the ground? So right here, I want to know how that theta is changing. Okay, so set up an equation involving theta. And I recommend that you use one of your trig functions that involves the hypotenuse. I think our book uses tangent, but that gets a little hairy with our derivative. So I'm going to use sine. The sine of theta is equal to x over 13. Opposite over hypotenuse. So really I have 13 sine theta equals x. Now take your derivative with respect to t. 13 times the cosine of theta times by d theta dt, which is what I'm looking for, equals dx dt. Well, 13, the cosine of theta at this instant, comes from that blue right triangle. 12 over 13 d theta dt is what I'm looking for. dx dt was moving at 2 feet per second, but it was negative. Okay, some algebra, the 13s cancel. So we have 12 d theta dt equals negative 2. So then d theta dt is going to equal negative 1/6. Now we need to think about units. Theta in calculus, remember, is radians per unit of time we get from the word problem, seconds. This related rate is a related rate. I call it a right triangle example. It's a good application. So we're talking about, in this example, a police cruiser approaching a right-angled intersection from the north and chasing a speeding car that has turned the corner, is now moving straight east. So we have an intersection, north and east. And our police car is up here, and let's call it the other car, C, is down there. When the cruiser is 0.8 miles north of the intersection and the car is 0.6 miles to the east, the police determine with radar that the distance between them is increasing at 15 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of that measurement, what is the speed of the car? So we're looking for the speed of the car. So we're looking for dc dt. I'm looking for that when a few things are going on. When the police car is 0.8 miles from our intersection and our car is 0.6 miles from the intersection. We know that the distance, I'm going to call this distance there d. We know dd dt is increasing at a rate of 15 miles per hour, because that's a rate. Miles per hour is a rate. And cruiser's moving 60 miles per hour. So our police are moving at a rate of negative 60 miles per hour. The reason it's negative is because he's moving towards the intersection. Okay, so let's write an equation for what we have here. We have an equation here. If I make that side of our triangle P and this side C, we have our equation to be P squared plus C squared equals the distance squared between them. So then I'm going to take the derivative with respect to time. Okay, so now you can divide everything by 2, so I'm just really going to kind of ignore these 2's in here. So now I'm going to fill in. Our police cruiser is 0.8 miles from our intersection. Our police cruiser is moving at negative 60. C is 0.6. dc dt is what I'm looking for. The distance. So the distance that's between them. Use this p squared plus c squared equals d squared, and that's going to end up being 1. And dd dt is equal to 15. Now it's just a matter of solving for this dc dt. I have negative 48 plus 0.6 dc dt equals 15. I go through, I'm going to go up here and solve for dc dt is going to end up equaling 105 miles per hour. Because I add the 46 over, then I divide by 0.6. Okay? So the cruiser, what is the speed of the car? The speed of our car is 105 miles per hour. That's super fast. Our next example is talking about a point on a curve. So a point is moving along a curve whose equation is given by that, and the point P is 2.5, and y is increasing at a rate of 2 units per second. How fast is x changing? So dy dt is equal to 2 units per second. We're looking for dx dt when our point on our curve is 2, 5. Okay, so we have our equation. Y equals x to the third plus 17. I'm going to put it to the 1/2 power. Now we need to find dy dt. So I find that we have a chain rule happening here. Remember that you're taking the derivative with respect to time. So your last part of your chain rule is dx dt, because I need to take the derivative of the variable x. Okay, so now it's a matter of just plugging in. We know dy dt is 2. X is 2. And I just noticed I made a little mistake here. I don't plug in 5. I was thinking about, you know what I was thinking about? Is I was noticing how I'm not plugging in y anywhere. So I ended up plugging in y by mistake. But notice how when I took my derivative, the derivative of y is just dy dt. So that y coordinate we don't even use. So now it's a matter of working through all of this. So I have 2 equals 2 cubed plus 17 square rooted on the bottom is going to be 5 times by 4, 12 on the top, dx dt. So solving for that, dx dt is going to be equal to 5/3 units per second. And that's how you would do an example where we have a point on the curve.